Hello, my name is Samuel Ang. I am a grad student at the University of Texas at San Antonio, and this is a presentation on GingerVR, an open source repository of cybersickness reduction techniques for Unity. Symptoms such as nausea and disorientation continue to plague users of head-mounted displays. Now, changes to headset hardware could eventually mitigate these issues through higher supported frame rates, or alternatively worsen them with higher supported field of view and higher supported visual detail. Now, researchers and developers have been hard at work creating new techniques to alleviate cybersickness on the software end, but unfortunately these techniques are not always widely available. So if I want to further evaluate a technique in a study of my own, I might need to implement that from scratch. Now that seems like a waste of time to us, so we present GingerVR, a software package of cybersickness reduction techniques for the Unity game engine. This package is open source, requires no dependencies outside of a stock Unity project, comes with instructions for ease of integration, and comes preloaded with 8 cybersickness reduction techniques inspired from the literature. Our goal is to create a central collection of these techniques to save developers and researchers their time. We plan to add more techniques to this package as they appear in the literature and invite others to do the same. A little more background here. There are some existing explanations behind the cause of cybersickness. Postural instability is one explanation. When in a virtual environment, there can be difficulty in maintaining an upright position, and this struggle could increase a user's level of cybersickness. Head yaw has been used to predict cybersickness in the past, lending some credence to this theory. Cybersickness may also be the result of a conflict between perceived motion through sight and the motion we feel in our body's vestibular system. Direct stimulation to the body's vestibular system has been shown to reduce cybersickness in the past, lending some credence to this explanation. Now, little is certain regarding why existing techniques are effective, but there are lots of different approaches to this problem, from rest frames, which offer a stationary position for the user to focus their attention on, to techniques involving the blurring or covering of the user's vision. Next, I will go through each of the 8 cybersickness reduction techniques currently contained in GingerVR. In 2018, Weinrich et al. Used a virtual nose as a natural feeling rest frame for users in VR. Our Unity asset, which is called Single Nose, can be dragged onto a virtual camera, replicating this effect. A number of settings can then be adjusted, controlling the size, positioning, and color of the nose. Our nose model was taken from Poly by Google. Now we noticed that this effect more closely resembled a large artificial nose on the front of the user's face more than their actual nose, something like a Groucho Marx mask for those familiar. If you close one eye and look at your own nose, you might notice that you're only able to see one half of it. So we created a variant of this approach called Authentic Nose for use with a dual camera setup. Each camera is serviced by its own nose model, visible only to that camera, and this variant comes with a spacing option which controls the distance between the two nose models. This next technique, inspired by Buehler et al., is called the dot effect. This asset suspends a matrix of virtual orbs around the user, which move at twice the user's velocity at all times. So if I move in any direction, it will appear as though the orbs surrounding me are moving away from me. This effect is meant to counteract a user's sense of perceived motion within the simulation. This technique can be a little hard to visualize, so please take a look at this demonstration. This asset comes with a number of settings controlling the number of dots surrounding the user and the sizing and spacing of the dots. Budhiraha et al. Were able to reduce cybersickness in users by applying a Gaussian blur to the user's vision in VR. The intensity of this blur is directly proportional to the rotational acceleration of the user's head, though an acceleration threshold must first be crossed for this effect to kick in order to ensure that the user isn't constantly dealing with a blurry image. Our script can be attached to a virtual camera and comes with options for an acceleration modifier, a minimum acceleration threshold, a maximum sigma or intensity value for the Gaussian function, and a smoothness value controlling how many times the effect is applied. One potential issue with the motion blur strategy is that it can obscure necessary information from the user. So for instance, if a user is in a driving simulation, we don't want to be obscuring the road signs from them. Ni et al. Proposed a salience-based cybersickness reduction technique to get around this problem, which omitted distinctive objects from the blurring effect with the help of deep learning. We noticed that these salient objects were often brightly colored, so we developed a color-based Gaussian blur asset of our own. By customizing a number of color threshold sliders in the editor, this effect can be told to ignore pixels meeting a certain color profile. For instance, if I wanted to ensure that stop signs were not obscured in a driving simulation, I could tell the asset to ignore pixels with a high enough red value. Fernandez and Feiner were able to reduce cybersickness through subtle field of view reduction. Our asset uses their approach and is implemented with a simple shader. As the user moves and rotates, their vision contracts at a rate determined by the formula below. Our asset contains options for the two modifiers in that formula, as well as a minimum field of view value and minimum thresholds for angular and translation speed. Farmani and Tether created a viewpoint snapping technique to reduce cybersickness in VR. When a user rotates their head at an angular speed past a certain threshold along the y-axis, their sight is blinded for a temporary period, as if they had closed their eyes for a brief time. Their viewing angle within the simulation is then snapped by a fixed amount. This hides the visual noise that the user would have ordinarily witnessed during the rotation, and prevents the user from rotating their head too far within the simulation in one go. This technique can be difficult to visualize, so please take a look at the demonstration. Our Vision Snapper asset can be customized to control the snapping angle, the minimum angular speed threshold, and the transition time. Kameni et al. Developed a head locking function for users in VR. Users could close one eye to lock their head within the simulation. The image displayed to them would remain the same even as they moved their head in reality. Our asset accomplishes the same behavior without eye tracking via a customizable key press. This behavior was surprisingly difficult to achieve in Unity. Our solution involves the use of a parent object containing all objects in the scene which need to be rotated. This is then rotated with the camera while the button is held. This currently may interfere with physics interactions, so we'll be on the lookout for a new solution in the future. To summarize, we have presented GingerVR, an open source software package currently containing 8 reduction techniques from the literature. These assets are easy to integrate and work with any stock Unity project. We plan to add to this package as more techniques appear in the literature and invite others to do the same. We hope that this software package can save researchers time and improve the consistency of these techniques as they are used in other studies. GingerVR can currently be accessed via our public GitHub repository linked in this slide. Here is our bibliography for this presentation. And if you're viewing this live, we can now open this up to questions.